Hello and welcome to Call of Chemistry. In this video, we will discuss about ionic equilibrium. We will cover all the concepts regarding this chapter. So let's start. So ionic equilibrium means where ions remains in equilibrium with the undissociated species. For an example, AB in solution state partly dissociates to A plus and B minus, where AB is a weak electrolyte. As AB is a weak electrolyte, then it partly dissociates to A plus and B minus, and after it reaches to equilibrium, then these ions recombines to give the undissociated species again. That's why we keep this reversible sign, and that is valid for only weak electrolyte. Then what is the scenario for strong electrolyte? Suppose AB is a strong electrolyte and it is in solution, it completely dissociates to A plus plus B minus, where AB is a strong electrolyte. So as AB is a strong electrolyte, then it completely dissociates to A plus and B minus. That's why we keep this single headed arrow. Now a question may arise into your mind that how can we find what amount of this AB will dissociate to A plus and B minus. We discussed that AB partly dissociates to A plus and B minus, but we don't know what amount of AB partly dissociates to A plus and B minus. So for this we have a law, that is Ostwald Dilution Law. Suppose AB is a weak electrolyte which partly dissociates to A plus and B minus, and here we write the initial concentration and at equilibrium. Suppose initially concentration of AB is C, then initially there is no A plus and B minus. Now when this reaches to equilibrium, then some amount of AB has been dissociated to A plus and B minus, and let's suppose alpha be the degree of dissociation. Then the concentration after dissociation or the concentration at equilibrium will be C minus C alpha. Suppose this alpha is 25%. Then what will be the amount of concentration at equilibrium of AB? Then it will be C minus 25 into C upon 100. So that's why the concentration at equilibrium of AB will be C minus C alpha. Then if C alpha amount of AB dissociated to A plus and B minus, then the same amount will be for A plus and B minus. So if C alpha amount of AB is dissociated, then the amount of A plus will be C alpha and amount of B minus will be C alpha. So here A plus will be C alpha, B minus will be C alpha. Now according to the law of mass action, the equilibrium constant K will be concentration of A plus into concentration of B minus upon concentration of AB. So if we put these values, then A plus concentration is C alpha and B minus concentration is C alpha, and AB concentration of AB is C minus C alpha. So K will be C square alpha square upon C into 1 minus alpha. So this C cancels out and we get C alpha square upon 1 minus alpha. Now as AB is a weak electrolyte, then the degree of dissociation alpha is so negligible. So alpha much less than 1. So 1 minus alpha nearly equals to 1. Hence this equilibrium constant K will be C alpha square, or we can write alpha square is equal to K upon C, or alpha is equal to root over K by C. So from Ostwald dilution law we get that alpha is equal to root over K by C, where K is the equilibrium constant and C is the initial concentration of the weak electrolyte. So from this equation we can see that if the initial concentration decreases, then this whole value increases, and so as alpha. So if the initial concentration of the weak electrolyte in solution decreases, then the degree of dissociation of the weak electrolyte increases. Now we will discuss the applications of Ostwald dilution law. So first application is determination of concentration of H3O plus of an aqueous solution of a weak acid. Suppose HA is a weak acid in aqueous solution, it partly dissociates to H3O plus and A minus. So similarly we can write here the initial concentration and the concentration at equilibrium. Suppose the initial concentration is C, there is 0 0, and concentration at equilibrium will be C minus C alpha. This is C alpha, this is C alpha, where alpha is the degree of dissociation. So if Ka be the equilibrium constant of HA, then applying the Ostwald dilution law we can find that degree of dissociation alpha will be root over Ka upon C. So from this we can see that concentration at equilibrium of H3O plus is C alpha. So concentration of H3O plus is C alpha, and if we put the value of alpha here, it will be C into K upon C. If we simplify this, it will be K into C. Similarly, we can find the concentration of OH minus in a aqueous solution of a weak base. So suppose B is a weak base and in aqueous solution it converts to BH plus OH minus. So how can this happen? We assume H2 as H plus plus OH minus, then as B is a base, is abstract this proton and convert to BH, and this OH minus is here. Similarly, you write here the initial concentration and the concentration at equilibrium. Suppose initial concentration of this base was C, then it was 0, Suppose at equilibrium the concentration of this BH is X, then the concentration of OH minus will be also X, then it will be C minus X. So X amount of this B combines with H2O to form X amount of BH and X amount of OH minus. So at equilibrium the concentration of B will be C minus X, and if K be the equilibrium constant, then it will be concentration of BH into concentration of OH minus upon concentration of B and into concentration of H2O. So we write K into concentration of H2O is equal to BH into OH minus upon B. So according to the law of mass action, the active mass of H2O will be 1 because H2 is in pure liquid state. That's why the active mass of H2 is 1. So it is constant. So we can write that Kb is equal to BH into OH minus upon B. We assume that the product of K and concentration of H2O is Kb. So if we put the value, this value, so concentration of BH is X and the concentration of OH minus is X and the concentration of B is C minus X. So it will be Kb is equal to X square upon C minus X. As the B is a weak base, so this X is much less than the initial concentration of this B. So X is much less than C. So we can assume that Kb is nearly equals to X square upon C. So here we find that in the aqueous solution the concentration of OH minus is X. So we have to find out the value of X. So from this we can see that X square is Kb into C. So X will be root over Kb into C. So far we have find out that in aqueous solution of a weak acid the concentration of H3O plus will be root over Ka into C, where Ka is the equilibrium constant of the acid and the C is the initial concentration of the weak acid. Similarly, the concentration of OH minus in an aqueous solution of a weak base will be root over Kb into C, where this Kb is the equilibrium constant of the weak base and the C is the initial concentration of the weak base. So these are the two very important relations. Now we will discuss the ionic product of water. So water is also an weak electrolyte and which dissociates as follows. Therefore, if the equilibrium constant is Kd, then it will be H3O plus into concentration of OH minus upon concentration of H2O whole square, because there is 2 equivalent of H2O, that's why H2O square. So we can write that Kd is equal to concentration of H3O plus into concentration of OH minus. Now as we mentioned earlier, the active mass of H2O will be unity because this is in pure liquid state. So this whole term is constant. So as this whole term is constant, we write this whole term as Kw is equal to concentration of H3O plus into concentration of OH minus. So this is called the ionic product of water. So concentration of H3O plus into concentration of OH minus is Kw So we put this value here and we get that Kd is nothing but Kw upon H2O whole square. So from this we have two important relations. Those are ionic product of water is nothing but concentration of H3O plus into concentration of OH minus, and Kd is Kw upon H2O whole square. Now we have to find the concentration of H2O. If we have given 1 liter of water, given 1 liter of water, and in this 1 liter of water we have to find the concentration of H2O. How can we find that? To find that, we have to assume that the density of pure water is 1 gram per cc. We all know that 1 cc is nothing but 1 ml. Density of water is 1 gram per cc. So can be written 1 gram per ml, as 1 cc is equivalent to 1 ml. So 1 ml contains 1 gram of water. So 1000 ml contains 1000 gram of water. That means 1 liter of water contains 1000 gram of water. And if we find the moles of H2O, then it will be 1000 upon 18 as molecule. If we calculate this, we will find 55.55. So the concentration of water will be 55.55 molar. That is 55.55 moles per liter. Put this value into here, so we get Kw upon 55.55 whole square, that is Kd. So this is an important equation. 25 degrees Celsius, the value of Kw is found to be that 10 to the power minus 40. Concentration of H3O plus into concentration of OH minus is 10 to the power minus 14 at 25 degrees Celsius. So we have discussed that the concentration of H3O plus and concentration of OH minus of an aqueous solution of a weak acid and weak base respectively. But if there are strong acid and strong base, then what will be the concentration of H3O plus and concentration of OH minus respectively? So concentration of H3O plus of a strong acid. Suppose you have given 0.2 molar H2SO4 and you have to find the concentration of H3O plus in this 0.2 molar H2SO4. So in order to find that H2SO4 in aqueous solution completely dissociates to 2H plus SO4 2 minus. So if as H2SO4 dissociates completely to 2H plus SO4 2 minus, so if the concentration of 0.2 molar H2SO4 is present, then the concentration of H plus in 0.2 molar H2SO4 will be 2 into 0.2 molar, that is 0.4 molar. We have supplied 10 molar NaOH solution and you have to find the concentration of OH minus in this 10 molar NaOH solution. Then we all know that NaOH in aqueous solution completely dissociates to Na plus OH minus. So if the concentration of NaOH is 10 molar, then the OH minus also will be 10 molar because it dissociates completely, and the equivalent of OH minus is 1, so here it will be 10 molar. If there is calcium hydroxide, then it will be Ca2 plus 2 OH minus. If 10 molar is given, then it will be 2 into 10, it will be 20 molar. So this is how we calculate the concentration of H3O plus and OH minus in aqueous solution of a strong acid and strong base respectively. Now we will discuss the concept of pH. So if you have supplied 0.0002 molar NaOH and you have been asked what is the concentration of OH minus in this solution, then you will tell the concentration of OH minus will be 2 into 10 to the power minus 4 molar. Now this is the inconvenient method of expressing the concentration of OH minus. Then what will be the solution? What will be the convenient way to express the concentration of H3O plus or concentration of OH minus in a solution? Scientist Sorensen expressed the concept of pH. He said that pH is nothing but minus log concentration of H3O plus and pOH is minus log concentration of OH minus. Now if the concentration of H3O plus is 0.0001 molar or 1 into 10 to the power minus 4 molar, then if we express in terms of pH, then pH will be minus log 4. So this is the convenience of pH scale. From the ionic product of water, we get that Kw is equal to concentration of H3O plus into concentration of OH minus. So if we take negative logarithm in both sides, then minus log Kw is equal to minus log H3O plus into concentration of OH minus. This term is written as pKw and this will be minus log concentration of H3O plus minus log concentration of OH minus. So from this we find that pKw is pH plus pOH. This is a very important relation. If we put the value of Kw here, we get minus log 10 to the power minus 40 is pH plus pOH. We get pH plus pOH is equal to 14. This is another important relation and it will be valid only for at 25 degrees Celsius. Earlier we found that concentration of H3O plus of a weak acid in an aqueous solution will be Ka into C and concentration of OH minus of a weak base in an aqueous solution would be Kb into C. So if we express this concentration into pH, what will be then? So H3O plus is Ka into C equal to the power half. If we take negative logarithm in both sides, H3O plus minus log K into C over half. So it will be pH, and it will be minus half log Ka minus half log C. So this is pH, and so minus log Ka is termed as pKa. So that's why this termed as half pKa minus half log C. pH is half pKa minus half log C. Similarly, OH minus of a weak base in an aqueous solution, that is Kb into C. So OH minus is Kb into C whole to the power half. If we take negative logarithm in both sides, log OH minus is equal to minus log Kb into C to the power half. So this is POH, and this is minus half log Kb minus half log C. So POH is equal to half pKb minus half log C. Also, we know that pH plus POH is equal to 14, which is at 25 degrees Celsius. So pH will be 14 minus POH. So from this, if we find pH, then it will be 14 minus POH, then it will be pH is equal to 14 minus half pKb plus half log C. Now we will discuss the relation between Ka and Kb. Suppose we take a weak acid, that is HF, and in aqueous solution it dissociates partly as H3O plus plus F minus. Equilibrium constant will be H3O plus into F minus upon HF. So the conjugate base of this HF is F minus, and in presence of H2O it forms OH minus plus HF. The equilibrium constant is Kb, then it will be concentration of OH minus into concentration of HF upon concentration of F minus. Concentration of H2O is constant because the active mass of H2O is unity, because it is in liquid state. That's why we ignore the H2O here. That is Kb is equal to concentration of OH minus into HF by F minus. So this is 1 numbered equation, this is 2 numbered equation. Multiply this 1 and 2, we get, so Ka into Kb, we get concentration of H3O plus into concentration of OH minus. So Ka into Kb is Kw. So again we write over here Ka into Kb is equal to Kw. Taking both side negative logarithm, we get minus log Ka minus log Kb is equal to minus log Kw. So this is pKa, and this is pKb, and this is pKw. So this is an important relation. Remember, at 25 degrees Celsius, pKa plus pKb is equal to 14, because at 25 degrees Celsius pKw is 40. Now we will discuss about common ion effect. Understand the common ion effect by an example. Suppose we consider acetic acid in aqueous solution and it partly dissociates to this, and if we add CH3COONA, which is a strong electrolyte in this solution of CH3COOH, then it completely dissociates to. Now we can see that in the solution of CH3COOH, this CH3COO- are in common ion. This CH3COO- is in large excess. So as CH3COO- is in large excess, then this equilibrium shifted towards left side, because now if this equilibrium shifted to left side, then the dissociation of CH3COOH to CH3COO- and H3O plus will be more reduced, then the weak acid will be more weak. So as a result of common ion, weak acids will be more weak. Now we solve a problem regarding common ion effect. So here we see that CH3COOH in aqueous solution dissociates as follows: CH3CO- plus H3O plus. And in this solution, in this acetic acid solution, HCl solution is added. HCl, being a strong electrolyte, dissociates completely to H3O plus. See that this is the common ion. So if we write this reaction separately, CH3COOH aqueous CH3CO- plus H3O plus. Initially, suppose the concentration of CH3COOH is C, then it is 0, 0 at equilibrium. So at equilibrium, suppose X amount of CH3COOH dissociates to give X amount of CH3CO- and X amount of H3O plus. So the equilibrium constant K will be concentration of CH3COO- into concentration of H3O plus upon concentration of CH3COOH. So we have to calculate CH3COO-, it will be Ka into concentration of CH3COOH upon H3O plus. Now we can see that in the solution X amount of H3O plus is already present. Then we add 0.1 molar of HCl solution. Then total concentration of H3O plus will be, total concentration of H3O plus will be X plus 0.1. As CH3COOH is an weak acid, then X is much less than 0.1. So this X can be neglected. then it nearly equals to 0.1. So if we put the values, we get the dissociation constant given as 1.8 into 10 to the power minus 5. So 1.8 into 10 to the power minus 5 into concentration of CH3COOH is 0.01 molar, 0.01, and concentration of H3O plus is 0.1. That is, so if we calculate this, it will be 1.8 into 10 to the power minus 6 molar. Now we will discuss the Henderson equation for buffer solution. We will derive the equation. Suppose acetic acid solution, aqueous solution of acetic acid is taken and it partly dissociates as CH3COO minus plus H3O plus, and if equilibrium constant is Ka, then it will be concentration of CH3CO minus into concentration of H3O plus upon concentration of CH3COOH. From this, if we determine the concentration of H3O plus, it will be Ka into concentration of CH3COOH upon concentration of CH3COO minus. Take negative logarithm in both sides. So minus log concentration of H3O plus is equal to minus log Ka minus log CH3COOH upon CH3CO minus. So from this we get that pH is equal to pKa minus log CH3COOH upon CH3CO minus. Then pH is equal to pKa plus log CH3CO minus upon CH3COOH. So simply we can write pH is equal to pKa plus log concentration of salt by concentration of acid. Similarly for bases, this is for acidic buffer. Similarly for bases, that is basic buffers, POH will be pKb plus log concentration salt upon concentration of base. The next topic is solubility product of sparingly soluble salts. I have made a special dedicated video for solubility product. I will give the link of this video in the description box. Please go and watch the video to know more about solubility product. So by this I am stopping here. If you have any doubt, please let me know in the comment section. Please like, share the video and subscribe my channel. Thank you.